Hello and welcome back to the Save It for Parts channel. In a previous video, I assembled and tested the MySat kit, which is a model of a 1U Cubesat, basically the smallest form factor of satellite that is typically launched today. This is a product from Ukraine that you can buy online, and it's one of the most affordable, if not the most affordable ways to get your hands on satellite-like hardware. This is a model. It is not intended to go into space, but it is only $300. There are other Cubesat analogs and simulators available out there for purchase or for assembly, but most of them cost quite a bit of money, and it really gives you a lot of the experience of designing, building, assembling, and testing a satellite. So it's a pretty cool project for STEM classes, for hobbyists, for universities, for anyone interested in space, in satellite design, or maybe pursuing a future career with NASA or another space agency. I'm not affiliated with the MySat project. This is not a sponsored video, and I bought this product myself, but I do think it's a very cool product, and I would really highly recommend it to anybody who's interested in space or satellite technology. Now, the MySat kit stays relatively inexpensive for several reasons. It's made largely from 3D printed parts, so a lot of the frame here you can print yourself. A lot of the parts that come with it in the kit are 3D printed, like the solar panel wings, like some of the mechanism on the top here, and you can actually customize the body, the shell, the fuselage of the satellite with your own home 3D printer. I believe you can also buy the 3D printed panels if you don't have a 3D printer at home, and you could get them printed at a university, at a library, or a makerspace, or somewhere else that has publicly available 3D printers if you don't have one at home and if you don't want to spend the extra money for the body panels. Now, 3D printed components are not necessarily space rated. They're made from extruded plastic. They're not really designed to hold up to the rigors of actual space travel. Things like vacuum, things like radiation, things like extreme heat, extreme cold. The layers can delaminate, the plastic can melt, and you can have other issues when you start to subject 3D printed PLA devices to environmental extremes like that. The electronics in here are also not necessarily rated for use in space, although very similar electronics have been launched in real CubeSats. So this is pretty close to what you would find in an actual launch-ready satellite. What if we could upgrade the MySat kit here? What if we could upgrade this satellite simulator into something closer to a real satellite that could actually fly in outer space? 3D printing company Prusa actually offers a space-grade polycarbonate filament. So this filament is designed to have low electrostatic discharge, low outgassing, high strength, low warping, high temperature resistance. Basically all of the things that you want in a space-rated material. I didn't mention the outgassing before, but that can actually be an issue not only because it weakens your material, but it can actually coat lenses, cameras, or other sensors in plastic particles and other stuff that comes out of traditional PLA when it's exposed to vacuum. Prusa's space-grade filament has been designed with an actual space company for making CubeSats, so it seems ideal for this situation. It is a little bit expensive. It's almost as expensive for a roll of this filament as it was for the Cubesat kit, but I think that might be worthwhile if it's actually going to survive in space. And I have a new 3D printer to try this out, the Prusa Core 1L. I've been using the Core 1L for a little while now, and I'm really impressed with it. The quality looks a lot better than other 3D printers I've tried, and there are a ton of other Prusament materials available, things like recycled algae, corn-based filament, there's some carbon fiber stuff, there is magnetic stuff, there are just all kinds of cool options with this. Another cool thing about Prusa's in-house filament is that you can scan a QR code on it and you can see all the technical specs of this exact spool, so you can find out how well was it manufactured, were there any issues, and if you have any issues in printing, you can kind of go back and do your own quality control. The cats also seem to like this nice warm cabinet, and that's why I've left the plastic on top here. I know I probably should peel this off, but I don't really need little kitty scratches all over the nice clear top. I've already been using it to print satellite antenna parts and accessories like this combination tripod and phone holder adapter for the Aero dual band antenna. Full disclosure, Prusa did give me the printer and the filament, although they're not paying me anything for this video. This is not a sponsored review, although I do really like the printer. Now, the only potential issue with using this on the stock Core 1L is because it is a high carbon polycarbonate fiber, it needs a hardened nozzle. And Prusa actually sent me a couple extra nozzles with this, so we have a regular extruder and a hardened nozzle. So I'm going to swap this into the printer. So replacing the nozzle is supposed to be pretty easy, but a few people online recommend actually printing a tool for this. And Prusa offers a tool because they offer a bunch of printable accessories and add-ons. So I'm going to go ahead and print this. And I'm actually just going to go ahead and do easy print. I'm just going to straight up print this from the website straight to the printer, which makes everything really easy. So I can set my printer, I can set my material. I'm doing the PC Blend Orange for this one. Everything looks good on the preview as far as I can tell. I'll put that in the center and we'll go ahead and print that. I'll switch over to that space grade filament. We'll tell it we've installed the hardened nozzle. Prints are going well so far. I'm noticing a few minor differences with this space grade stuff compared to regular PLA or the PC Blend that I've used before. It's a little bit stiffer, it's a little bit stronger, so I do have to pop this out. And then it leaves quite a bit more stringing, and it's actually kind of hard to break this. I've had to use the clippers in some cases to clip off some of the excess stuff. The quality is overall pretty good. I'm noticing there are some little bits of stuff stuck to it. There are like some little dribbles of filament on here, so it might need a little bit of sanding, possibly more sanding than some other materials I've tried, but yeah, overall, decent quality. Also still reasonably flexible while remaining strong. Alright, so that should be all of the structural frame elements of the MySat kit, now printed in polycarbonate space grade. So we can start replacing the PLA frame that I printed before. Now, I did not do this top solar framework for a couple reasons. First off, it's very complicated and there are a lot of small pieces in here. This actually came pre-assembled when I bought the kit, so I don't know if I can easily get this apart and back together without breaking something. Second reason is the solar panels are actually glued onto these wings here. Yeah, it's not super easy to separate these. Now, the solar assembly here is kind of an optional add-on that they sent me, and it's not really necessary. It's cool, it's an extra feature, it's an extra moving part that kind of adds to the interactivity of the satellite, but these panels can actually fit, I think the solar panels can actually fit within the top and bottom framework, and you can have a more traditional streamlined CubeSat where you don't need this fold-up mechanism. I printed an extra plate, just one of the blank plates that replaces the top solar plate, so I don't necessarily need this. I might just take this off, and I don't necessarily need the solar panels for testing either because there is an internal battery and it can run off of that for all the tests that I want to do. And so far I'm pretty happy with the quality of the Prusa space grade filament. Everything seems to fit together pretty well. I had some issues when I did the PLA where some of these inserts wouldn't clip into their respective panels securely. The precision and fitment on the Prusa Core 1L parts definitely seems better than the PLA parts that I previously made. Yeah, there's some bulging here and there. There were some pieces I had to cut to make them fit. You can't really tell from a distance, but I wasn't 100% satisfied with how all the parts went together on this. All right, let's get this thing broken down and reassembled. All right, here is our new and improved space-rated CubeSat, or at least the enclosure is space-rated. The electronics are still kind of off the shelf, and I'm not sure about the battery, so I don't know if this would actually survive in space, but I'd like to test that next. Now, I did notice this high-carbon polycarbonate 3D printed material actually does mark surfaces. There's there's carbon in it. It's like pencil lead, so I've got these little marks on my bench surface. But otherwise, this seems about the same to work with as regular PLA. I had one or two frustrating moments in the assembly when things like these little square nuts didn't quite fit, but honestly, that was the same with the PLA prints. Those nuts they're really tight in there, and they're supposed to be. You have to almost hammer them into place so that they'll stay, and then you can attach the rails and the sides with the screws all the way around. It definitely looks different than the old one. I had red PLA before, but now it's all black because that's the only color I have in the space-rated material. Yeah, it looks a little bit different. I don't know if that would cause any different thermal loading in space where you've got direct sunlight versus the red and black that I had before, and I don't know if there's another color that you would prefer. I think since most CubeSats are made out of metal and not necessarily painted, that yeah, there's not a lot of color variation in some of the commercial ones. So how are we going to test the MySat space-rated version for space? Because I can't launch this. It still costs $10,000 to $50,000 to launch something this size, and I don't think a commercial space company is going to launch a kit like this because it is, again, not really space rated, but I'd like to test it in as close an environment as possible. So I'm going to attempt to test this in vacuum, in extreme cold, and extreme heat, or at least as much as I can do at home with those environments. Real launch and spaceflight would also involve heavy vibration, which I may or may not be able to test, and potentially high radiation, which I cannot test at home, but I can test some of those other things. So out here in the garage, hoarded between the airboat and the propane tanks, I actually have a vacuum chamber. This came from Axeman Surplus, my favorite local Twin Cities store. I have never actually used this thing, and I think it is going to need a little bit of setup and adjustment. Now I'm also going to need a vacuum pump, and I have a couple of those too, just hoarded away in the garage. Again, I've never used them, but you know, vacuum pump seemed cool when I came across these for free, so I said, yeah, I'll take those. I think I even have some special vacuum pump oil up here with the outboard parts and oil. And I've got this bin of random pressure and vacuum hoses and whatnot. I found this gauge that goes from 0 to 15 psi, and I think vacuum is like 14.7 psi different than regular surface air at sea level. So I'm gonna see if I can mount this gauge inside the vacuum chamber and run it out, so we'll have the external air pressing on it, and then it should read up to about 15 if we've got a full vacuum. And then maybe I'll put a GoPro or something in the vacuum chamber. I don't know if that's gonna work. I don't know if that's gonna ruin the GoPro, but I'm gonna give it a try. I could also use the built-in camera on the satellite, but I think that it's going to have trouble getting a signal through the metal vacuum chamber, so I'll probably just have to record everything in there and then look at the video later. I'm also trying to find adapters to go to the fittings on the vacuum chamber and on the pump. I decided to use this one because it already has a hose and a gauge on it. I will also probably need some kind of gasket to go around the rim of the vacuum chamber, and then it gets bolted down. Fortunately, these are standard bolts, and I found some that match, but I suspect this is going to take a few tries to get a good solid vacuum inside of here. Okay, amazingly, this seems like it's working. I do not have a proper gasket on this, so I basically just clamped it down and then duct taped around the seam. And this is the inlet for my interior pressure gauge, which maybe the GoPro is seeing if this is working, and if the GoPro hasn't died, and if my flashlight hasn't died. The vacuum pump is now making bad noises. Against all redneck engineering odds, I think I may have actually pulled a vacuum inside that chamber. We definitely have a leak somewhere. I can hear it hissing around my finely crafted duct tape seal. Let's get this opened up. All right. Well, the GoPro is still working. So the GoPro showed that we got an atmospheric pressure difference of about 13 psi. Now, I'm not at sea level, so my local atmospheric pressure is something like 14.3-ish. So we didn't quite go to full vacuum, but running this through some calculators online, it looks like we got the GoPro to a simulated pressure altitude of something like 50,000 feet, maybe a little bit more. I'm actually really impressed. I did not expect the vacuum chamber to work right away, especially with my redneck pipe fitting and my redneck duct tape gasket. I'm gonna try an electrical tape gasket because I think that'll make a little bit better seal. And then maybe we'll run the vacuum pump longer, try to pull out a little more air, and try to hold that pressure down a little bit longer. We'll try the GoPro again and we'll see what it looks like this time. That time I left the vacuum pump on for a half hour. It's actually really hard to get the dive case open on the GoPro now because it's vacuum sealed. It's pulled all the air out of here. And yeah, I basically have to pry this open because the inside of the case is under vacuum. All right, we got it. The pressure gauge and the camera weren't quite lined up, but it looks like we got down to negative 13.5 psi. So again, looking at online calculators, that's close to 65,000 feet of effective altitude. So I've got the MySat set up in the vacuum chamber. I've just got it perched on an old tripod right now so that it's up at the right level where the GoPro can watch both the satellite and the pressure gauge. So we're getting telemetry data from the satellite before it goes into the vacuum chamber. All right, we're having some issues with the seals around the pressure gauge. So yeah, my little rubber gasket there keeps kind of slipping in. All right, we're trying this one more time. I've got a different gasket on my pressure gauge inlet. So I'm going to leave the vacuum pump running for another half hour just to maintain the vacuum inside the chamber. I'm hoping that the battery lasts on the satellite and on the GoPro. And we'll just have to come back, crack it open, and see what we got. All right, I think that's been under vacuum long enough. Let's pop it open. I could not receive any telemetry from this while it was inside the can, but I sent it some commands over the serial radio. I told it to turn on this big LED. And it looks like it turned on. Yeah, so we were actually able to transmit some commands to the satellite while it was inside the vacuum chamber. That was pretty cool. And yeah, the satellite seems to still be functioning. It was able to accept and execute that command. So it's probably been transmitting telemetry the whole time, but my laptop was not able to receive it until now, until it's out of the vacuum chamber. And it looks like everything is still functioning. It would have been interesting to record that pressure while it was in there. The current firmware on the satellite, I think, does not do any recording, but maybe I could figure out a way to do that and save it onto an SD card. So I was trying to use some of this Teflon tape to seal the connection around the pressure valve, and some of it actually got sucked into the vacuum chamber and wrapped around the satellite. That might be interesting to see if we can spot that happening on the GoPro footage. I wanted to see if I could boil water in this vacuum chamber, even though I know the pressures involved are a little bit marginal for that. So we didn't get a real rolling boil, but we did get bubbles forming in the water, and then we did get some bouncing around at the surface, which is kind of where I would expect the boiling to happen at the interface between the vacuum and the water. And looking online, it looks like water does start to boil at room temperature around 0.02 atmosphere, so a little bit lower than I thought I was going with the pressure gauge, so an equivalent altitude of something like 80 to 100,000 feet. I think we'll move on from the vacuum chamber, and next we'll test out the MySat at low temperatures. In space, you get huge temperature swings between freezing and boiling because sometimes you're in direct sunlight and sometimes you're in shadow behind the Earth and you're not getting any sunlight. So we have to figure out if the MySat can handle that. Can it go from freezing temperatures to very hot temperatures and back and forth? So let's just stick it in the chest freezer for a while. After a few hours in the freezer, this seems to be just fine. It doesn't feel any more brittle than before. I've been kind of poking and prodding at the narrow bits here, the thin parts, and nothing's snapped. So yeah, I mean, it's nowhere close to the cold of space. I guess that's about as close as I can get without getting some kind of crazy industrial or scientific freezer. For the next test, I'm going to stick this under multiple heat lamps and leave it for a while. Now, this isn't super realistic either, because in actual life, usually these satellites are tumbling. They are spinning to some degree, so they're getting more of a rotisserie effect. They're usually not getting heated up on just one side. But I don't have a good all-axis rotisserie system. I could just put it on a motorized platform and have it spin around, but we're just going to see what happens if we aim the heat lamps at one side for a while. That should give it the most exposure, and we'll see if anything gets soft. We'll see if the electronics complain or if we have any other issues. I went straight from the freezer to the heat lamps, so we're watching the temperature rise pretty quickly here. All right, we've had this sitting for a while, and it seems like it's kind of peaked at 70 degrees Celsius. It goes up and down a little bit, but it's kind of staying in that 70-degree range. So I think that's about as hot as I can get it without putting it in my oven, which I thought about, but I don't really need to reflow the solder, and I don't really need the oven to smell like warm plastic, especially if something goes wrong. And again, it's not really realistic to have the entire thing heated up this way. In orbit, in real life, a satellite would be tumbling and it would be heated kind of inconsistently. Boy, it definitely smells like overheated electronics. Some of the 3D printed structure is a little bit looser than before. It's definitely not melting yet, but yeah, it might be getting close, especially the parts that were almost touching the heat lamp. The actual temperature sensor is kind of down in the middle, so the outer structure, I think, did get a little hotter than the sensor itself. Actually, not that much different in temperature than the other piece. So this was the regular PLA. This was the same distance away from the heat lamp as the space-grade polycarbonate was. And obviously it did not fare as well. So this definitely got hotter than 70 degrees Celsius, because it takes more than that to melt PLA. So I think it was definitely a lot hotter at the point that the actual hull of the Cubesat was up next to the heat lamp, and the sensor was down inside, so it was not registering the actual temperature on the outer fuselage here. All right, to put the original pieces in the chest freezer for about the same amount of time as we did the other one, and yeah, still not brittle. It's still pretty flexible. I was a little bit worried that this would get brittle and snap, but it's doing okay. So in case you think I'm some kind of expert at any of this, here's a story that will change your mind. I just put the PLA materials into the vacuum chamber to do another test with the GoPro, thinking that maybe if enough material outgassed from the PLA, maybe I could see the GoPro lens getting a little foggier or something, or I could scrape something off of it at the end. I knew that was a long shot. I knew there probably weren't enough particles outgassing from the plastic to be instantly visible, but I wanted to try anyway. And I forgot to put a light source in the vacuum chamber, so this entire test was in the dark. Now, looking at the video from the GoPro as I put it into the chamber versus when I took it out after pumping down the PLA material, maybe it looks a little bit foggier. I did wipe the lens off and I didn't see any material on there. I didn't see any kind of coating of plastic, but again, it's going to be such a small particle density that it will probably be really hard to tell. So this one was pretty inconclusive. I think if you had scientific sensors, if you had an extremely high accuracy lens system that had to be 100% clean, then yes, you would not want plastic, you would not want PLA, you would not want materials that could outgas particles onto your clean sensor surface. But again, for my kind of home testing rig, I think this is something that would be really hard to detect. So one other thing I found about this kit is that the default little antenna on here on the serial radio module is kind of terrible. It doesn't go very far. And I actually put a length of wire on here for some of the tests, and that gave me a lot more range. That let me talk to this thing inside the freezer. I could actually talk to it. I could get data onto this, and I could send it commands inside the vacuum chamber, but I couldn't get telemetry back out even with a longer antenna wire. Yeah, in real life, you would have something like a spring-loaded antenna or a tape measure that pops out, and that would give you a little bit better reception from the ground when listening for the telemetry from the satellite. So the biggest difference I've seen with the space grade polycarbonate is the heat resistance. Again, I had the PLA and the space grade stuff the same distance away from the heat lamp, and this is what happened to the PLA. The polycarbonate here just has a tiny bit of warping kind of on this edge, which was the closest area to the heat lamp. So yeah, a lot more heat resistance here than here. Well, I think that about wraps up the tests that I had in mind for the MySat kit, now upgraded with the space grade filament. And yeah, I'm pretty happy with this. It's cool to have a theoretically space-rated frame around the MySat. Now, there are other tests I could do that I didn't do in this video. I could do a vibration test. That's something I could probably rig up some sort of shake table hooked up to, like, I don't know, an old gas engine or something to shake this apart to see if the modules would pop out. And I suspect the modules would pop out because they're basically just seated onto the PCB. If I wanted this to be a little stronger, I could epoxy things in place, but I'm not quite ready to do that yet because I'm still experimenting with this. So we might leave that test for a future time. Radiation test, I don't have access to a good radiation source, so I can't exactly blast this with solar radiation. The heat test, I think, went really well. We definitely saw a big difference between the space grade Prusa and the regular old PLA at the same distance from an infrared heat lamp. For the cold test, we didn't really see a lot of difference with the actual material, and the satellite itself worked just fine down to about -20 Celsius. I'm also super happy with how the vacuum chamber came out. That thing was really cool, and I have a few ideas in mind for other tests and experiments to do with that vacuum chamber. So you might see that showing up in future videos, and if you have any ideas for the vacuum chamber, let me know down in the comments, and you might see those ideas pop up again. Now again, I need to stress, I am not an expert, I am not a satellite builder, I'm not a rocket scientist. I am just a guy with some junk in their garage, and none of these tests really got to actual space conditions. We got down to about 1/20th of an atmosphere, or an equivalent altitude of something between 65,000 and 100,000 feet. So that would be something like sending this up with a high altitude balloon, which could be something to do in the future. I believe the MySat folks are developing a kit to put this on a balloon, to send it up to a near space environment, as a lot of the balloon people like to call it. And I was able to send it to a near space environment here in my garage with the vacuum chamber, with the heat and the cold. And again, actual space conditions can be between 200 degrees Celsius and -200 degrees Celsius. So my little test of going between 70 degrees C and -20 was really not that close to space conditions, but it's as close as I can get here. I would like to put the solar panels back on here for some future tests, and that's going to require me to maybe peel these off of the original PLA panels and maybe reprint and reassemble this solar deployment module that looks really complicated, but I could probably get this figured out if I gave it some time. I just don't have time for it in this video. I could also do a better antenna system. It would be cool to have a deploying tape measure antenna on this, maybe with some kind of little commandable release so that the tape measure remains folded up around the satellite and then pops out into position. That's something we could try to do in the future. It would also be fun to mess with the code on the MySat. I didn't do any alterations to the original firmware with this, so I was just running off of what MySat sends with it, what MySat has on their GitHub page, but some other features might be cool. Maybe something like SSTV to transmit live images over the radio module from the camera. Right now the camera is set up to send over Wi-Fi, which isn't very realistic for a space environment, but sending over SSTV would be kind of fun. Also storing and downloading telemetry or images later would be kind of interesting. Right now it just sort of live dumps the telemetry as it goes. It doesn't seem to store anything. And that would be really helpful for putting it in the vacuum chamber where the tiny little radio in here is blocked, and that would actually approximate space conditions, because if you are a single ground station, you're only going to see this satellite for about 10 minutes of its 90-minute orbit, assuming it's in a polar orbit. And yeah, you're only going to get basically 1/9 of the time of the orbit to download all the data from the rest of the satellite's journey. Anyway, I think this was a fun video. It was really fun trying to approximate some space conditions here at home. I really think the MySat kit is a lot of fun, and if you want to check it out for yourself, I will put links down in the description to their website. Even with shipping costs and delays from Russia's war, even with inconsistent tariffs, even with the expensive Prusa filament, this is still cheaper than any other Cubesat kit that I've seen on the market. I will also put links to Prusa and the space grade Filament down in the description, so if you want to check those out, I would also highly recommend those. I've had a lot of fun with the Prusa Core 1L. I have really liked the quality on its prints, I've liked the speed, I've liked the heat consistency, and it's just overall been a very nice printer, especially compared to some of the other brands I've tried. So thank you again to Prusa for supporting this video. Thank you to Axeman Surplus for supplying the vacuum chamber. Thank you to all my Patreon supporters out there who really help out the channel and help me buy parts and equipment for interesting projects like this. If you'd like to see future Cubesat or other satellite projects, make sure to subscribe so you don't miss those, and you can always go back and check out the earlier video reviewing the MySat kit. And finally, thank you to everyone out there for watching, and we'll see you next time.